Hi everybody, and welcome to a bonus lecture for Phil 2002, Logic, How to Defeat Your Foes with Reasoning. I'm going to talk to you about an interesting feature of propositional logic called functional completeness. In fact, this is a feature of all logics, but for our purposes we want to just focus on its application to propositional logic. And functional completeness is really interesting because I think it gives you a deeper insight to how truth tables work, how the semantics work, and how each of the connectives work in our language. It's also going to help you to work out some of the harder questions on your assignments, problem sets, and the exam. All right, so let's get started. So functional completeness relates to the various different connectives that we have in the language of propositional logic. So far what we have are just a handful of connectives. So if we think about the connectives that we've got the AND connective, we've got the OR connective, we've got the arrow connective, we've got the biconditional connective, and we've got the negation. Now what we can do is we can actually draw a truth table up that situates all of these things into a single truth table and gives you an example of each. So I'm just going to do that because it's going to help us to see something really interesting about the logic. So I'm going to start with the matrix with two propositions. So I've got A and we've got B. Oops. Start again. We've got A, we've got B. Being non-compliant. Okay. All right, so there's our beginning matrix, and we're going to just put in our T's and our F's. What I'll do now is I'll just put in each of those four connectives inside the truth table. So we'll start with A and B. And then A or B, A arrow B, and then A biconditional B, and then just not A. Now when I introduce these things to you, I introduce them to you as little boxes that you feed information into and then you get some information out. So you've got the negation box, and into the negation box you feed the values for A, and then it spits out some value for the not A. So if the A is true, then it spits out that not A is false, and if A is false, then it spits out that not A is true. Similarly, if you've got the conjunction box, you feed in values for A and B, and then you get some information out about the conjunction A and B. So for instance, if you feed in that A and B are true, then you get out the information that the conjunction A and B is true. When you feed in A is true and B is false, you get out the information that A and B is false, and so on. Each of these things you can imagine as a box. Now what those boxes actually are things called functions, and functions are just things that have inputs very roughly and that give some output based on something that happens inside the function. If you've ever done linear algebra or studied differential equations or anything like that in mathematics, you'll probably be dealing with certain functions. If you do calculus, you deal with functions. Those are much more complex functions than the functions we're dealing with, but we're still dealing with functions. Now, we've just got here basically 5 different functions. We've got a conjunction function which takes in information about A and B, then spits out some result for A and B. We've got a disjunction function, a conditional function, a biconditional function, and a negation function. And our language, as it stands, the propositional logic that I've defined, only has these things syntactically defined in it, and semantically we just focus on these 5 truth tables and then apply them broadly to more complex propositions. But those complex propositions are still just going to be a basic function of these 5 truth tables. But if you look at this space of truth tables that we've got here, and think in terms of what a truth table is and the kinds of information you can get inside a truth table, we can start to see that there are other possible functions that we could have. So here we've got 4 possibilities, right? And our function yields some kind of some combination of t's and f's in a single column for the relevant possibilities that we feed in. And you can see that each of these columns is distinct. Here we've got a t followed by 3 f's. Here we've got 3 t's followed by an f. Here we've got a t, an f, a t, and another t. Here we've got a t, an f, a t. Here we've got an f, a t, and a t, right? So each of those columns is distinct. Now, if we imagine all of the sort of columns that there could be, we can start to see that there are other possible combinations in that sort of vertical column that we could have. So we've got t followed by 3 f's. We've got 3 t's followed by an f. We've got a TFTT, we've got a TFFT, and we've got an FFTT, but we don't have, say, a TTFT, right? That's not listed in this set of columns that we've got for these propositions. We don't have an FTTT. We don't have FTTF, right? So there's a range of different functions that we could actually put into these truth tables, but that we haven't. So let me just draw some of those down for you so you can see what I'm talking about. So I'm just going to repeat, this is just meant to be 2 truth tables squashed on top of each other. I'm going to put the matrix back in for the A and the B. Okay, and now I'm going to write down some of these alternative columns that I was just describing. So one of the ones that I described was one that says FFFT. So I'm going to put that in. Another one was TTFT. Another one was FTTF. And we can imagine still more that we haven't even listed here. So what we could do, for example, is have one that is just all T's. And we could also have one that's just all F's. All right? So that gives us 10 different combinations. Now with the propositional logic, we've got names for these first 5 combinations. We call this one a conjunction, we call this one a disjunction, this one a conditional, this one a biconditional, and this one a negation. But I haven't given you names for these other 5 down here. Let's just number them for now. I'm going to start at the top. I'm going to call this one number 1, this one number 2, this one number 3, and so on. I'm just going to number them all sequentially. Right, so what we've got there are 10 different things. And these 5 up the top are boxes that we're familiar with. We know these functions, I've introduced these functions to you, and you've seen how to use them. But what we've got down here are 5 completely different functions that we've actually never seen before. And these 5 different functions we haven't named, we haven't introduced a symbol into the language in order to represent. Now here's the interesting thing. We really could, if we wanted to, introduce symbols for each of these and then work with them. So for instance, we could call this thing, we could just introduce a star for this thing. We could introduce a heart for this thing. We could introduce a smiley face for this thing. We could introduce a box for this thing. We could introduce a diamond for this thing, and so on. We could just introduce these new symbols, and then we could put propositions in as functions of those things. So we could have A, heart, B, and we could actually add that into the language as a new syntactic item and then work with it if we wanted to. So there are a couple of interesting questions that arise at this point. One question is, why don't we use these other things down the bottom here? And the other question that arises that's interesting is, I've got 10 of these things written up. How many are there in total? Okay, so to the first question first, why don't we use these things down the bottom here? The reason we don't use these things down the bottom here is because they don't obviously represent things that we're interested in when we're trying to work from English arguments into the propositional logic. So we've chosen a select group of functions that are really useful for mapping the logical structure of arguments, but we don't tend to need these other functions in order to do the kind of mapping work that we're interested in doing. Sometimes you might need these other functions, and there might be situations in which introducing these functions into your language and working with them is a really useful thing to do. But for the most part, we don't actually need these things, and so we don't focus on them. But we could easily introduce them into the language and work with them in just the same way, because notice that each of these values here is still a direct function of what's going on over here. So for instance, when we look at the one that's all t's, what that's telling us is that no matter what values a and b have, the symbol that connects them, so if you had a box b like this, then that would be always true. In some of your assignments, you have a box later on. That box is going to be redefined in a different way. So don't take any of these random symbols that I've introduced here as always locking onto these definitions. I'm just using them now for this case, for these examples. They'll be used for other things later on. So don't get caught up in the symbology that we're using here. All I want you to focus on is the fact that we could, if we like, introduce some new symbol like this and thereby introduce a new function where it takes in values for a and b and then spits out some result. But we just don't tend to focus on these 5 down the bottom because we don't need them for modeling arguments. The second interesting question, which was how many of these things are there, can actually be solved fairly easily. One way to solve it is to brute force it, and you can brute force it just by trying to write down combinations until you run out of distinct combinations to write down, at which point you will have written down all of the functions that there are. The other way of working this out, which is a little bit more complicated, is to use some features of combinatorial mathematics in order to work out the possible combinations. And there's going to be a fairly straightforward function that defines how many possible combinations there are as a function of the number of basic propositions that are being fed into the relevant connective that you're interested in. Okay, so if you want, you can sit there and work out all of these possible combinations. I invite you to do that. But just to sort of read the last page of the book first, the number of possible combinations here is 16. There are 16 functions of this kind for propositional logic. 16 distinct functions. We use 5 of them to actually build the propositional logic and model arguments, but there's another 11 of them that we actually don't tend to use, but that we could use if we were expanding our language further. Of these, the one that is actually probably the most interesting, or the one that is sometimes actually used in logic, is one that I do already have up here, and it's this one here. So this one where it's FTTF. Remember earlier on in the course I introduced a distinction between an inclusive and an exclusive disjunction. An inclusive disjunction is where you say either A or B or both. An exclusive disjunction is where you say either A or B and not both. You can't have both of these things happening at the same time. You can only have one or the other. If you look at this thing here, this thing is a good representation or a good function for the exclusive disjunction. It's sometimes in computer science terms called XOR. This thing is sometimes called AND/OR. All right, so if you look at the values that feed into this function, you'll notice that when A and B are both true, then this thing is false. And when they're both false, then this thing is false. But when exactly one of those is true, then this thing gets to be true. So it's only ever true when one of those is true, and it requires one of them to be true, which is the sort of thing that we would expect from an exclusive disjunction. If it's either the case that A or it's the case that B, but not both, then we should expect it to be the case that the function would look something like this. So some of these are useful. Some of these are introduced, for instance, in computer programming and software engineering. You're very likely to have the XOR. We don't typically have it in propositional logic for reasons I outlined earlier in the course, namely that in terms of natural language arguments that we put forward, we typically use the inclusive disjunction. But in computer software engineering, you might well want that exclusive thing so you can rule out this case where both A and B occur. All right, given that there's 16 of these things, there's another interesting question that arises. And the question is this: how many of these functions can you use to produce the rest? So what do I mean by that? Well, one thing you can do, once you sort of notice that you've got these 16 different combinations and you think about the fact that you can also combine these to produce new propositions, is you can start to try and build some of these functions out of the functions that you've got. So let me just give you an example of how that works. So let's think about the XOR, the exclusive disjunction that we're just talking about. Have a look at this. Okay, so I'm going to start with the truth table for the biconditional. Remember the truth table for the biconditional, they're standing or falling together. And now what I'm going to do is I'm going to use the biconditional in combination with something else we've already got, the negation, in order to produce the function for the exclusive disjunction. To do that, it's pretty straightforward. I just take the biconditional and I negate it. If I take the biconditional and negate it, then I'm going to reverse the true values that are over here, because that's how the negation works, and I'm going to end up with the exact column that corresponds to the exclusive disjunction. So this is what I mean by building some functions out of others. We can build the function for the exclusive disjunction out of the biconditional in combination with the negation. So we've got all 16 functions. Is it possible to build all 16 with less than 16 total functions? And how many of those functions can you, if you want to build all 16, how many functions do you need in order to produce all 16 of those functions? So if you've got, how many basic parts do you need in order to do this trick where you build all of the other functions? And the answer to this question is actually quite surprising. First of all, there isn't just one answer. So there are multiple, in some sense there is just one answer. There is a minimum number of objects that you need, but exactly what those objects are, there isn't just one case for that. There are lots of sort of minimal sets of objects that you can use to produce all of the functions that you need. So here's one group of objects that you can use to build all of the other functions. If you just have the negation and the conjunction, then you can build all 16 of those other functions using just these two things. Now, you can prove this. There are sort of proofs outside of logic that allow you to show this fairly straightforwardly, but I'm not going to prove that for you. Instead, I'm just going to give you a sense of how you might do this by building all of the standard connectives that we've got, the disjunction, the conditional, and the biconditional, just out of the negation and the conjunction. All right, so the only things I have available to me are the negation and the conjunction. I've got to put those together in combination with A and B to come up with a column that looks like the conditional, a column that looks like the disjunction, and a column that looks like the biconditional. I'm going to start with the disjunction. So what I want is something that ends up being true, 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 false, which is what the column for the disjunction shows you. So if I've got not all right, so have a look at that statement. It's not the case that not A and not B, right? So I've got a negation right out the front. I've only used negations and conjunctions. Now let me compute this sentence for you. I'm going to go flip the values for the A's and the B's when I'm negating them. And then I'm going to use the conjunction. And then I'm going to use the negation. And it didn't quite get what I wanted. So it turns out that I had it the first time. I didn't need to add that extra negation. So if I just go back a couple of steps, what I ended up with was false, 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 true. But what I wanted was true, 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 false. And in fact, I had that. Earlier on. So let me just do that again for you. Okay, so I've got the negations, then I just do the conjunction. Sorry, I did have it right the first time. As you can see, this is not a precise science. Sometimes it requires a little bit of trial and error to get it right. So I did have it right the first time, I just messed it up the first time. So I do the negations for the A and the B first, then I do the conjunction, and once I've done the conjunction, I then do the next negation, and I end up with a final column here that says TTTF. So this statement is equivalent to the disjunctive statement. So I've been able to build the column for the disjunction using just negations and conjunctions. And once I've got the disjunction, I can start to do the same for each of the other sentences that I might want. So now I'm going to try and produce the conditional statement. And in order to produce the conditional statement, I need something that says TFTT. Okay? So let me just do that for you. Okay, I think this should be right. So I'm going to do the negated B first. Alright, so what I did is I did the negated B and I just put in the values for A. Then I determined the conjunction by working out the values for the conjunction based on the negated B and the A, and then I negated the whole thing. And what I ended up with is a truth table that's exactly the same truth table as the conditional statement. Now, if I want to, the last one I need to produce is the biconditional. In order to produce the biconditional, what I need to do is produce something that is goes true, false, false, true. Okay. Now, in order to produce something along those lines, the most straightforward way to do that is to combine two conditionals. The biconditional, after all, turns out to just be the conjunction of two conditional statements. But I need the conditionals going in both directions. That's what the biconditional tells us, that the conditional goes in both directions. So if I can build the two conditionals going in both directions and then combine them with a conjunction, then I'll end up with something that has the right kind of truth table. So I'm just going to rub this out so I can build the last one for you so you can see how this works. Alright, so what I want to do here is I want to build the biconditional. I'm going to start with the conditional that I know that I have because I already built this conditional. And now I'm going to add to that a conditional going in the other direction. And that should look like this. And I'm going to put a conjunction between them. And hopefully, see there's just negations and conjunctions in here. Hopefully I should end up with a truth table for the biconditional at the end. So let's see what happens. So I do the negated B here first. Then I put in the values for A. And then I do this conjunction. And then I do this negation here. Oops. And I get rid of those values in there. Now I move over to the right-hand side of the conjunction. I put in the values for B. And then I do the negation for the conjunction. Okay, now I've got two sides of the conjunction, and I'm going to work backwards to that middle conjunction in order to solve the entire problem. And I've got TT, so I get a T in the middle, FT, so I've got an F in the middle, TF, so I've got an F in the middle, TT gives me a T in the middle. I cross off these values, and then I look at what I've got. I've got the truth table for the biconditional. So what I've been able to do using just the negation and the conjunction is build the conditional, the biconditional, and the disjunction as well. And so it turns out actually that that gives me 4 different functions that I can build. I know that I can build the conjunction function, and I can build the other 3 functions, those other 3 functions that I just built. I've also got the negation function, so that's a 5th function that I've got. Can I build the other 11 using just the negation and the and? It turns out that I can. So the negation and the and can be used on their own, just those 2 functions, to produce the full range of other functions that there are inside this sort of truth table structure that underlies the propositional logic. What we call that set then, just the set of these 2 connectives, we call it a functionally complete set. using just these two connectives, I can build all of the possible functions that you can use with respect to A and B in propositional logic, and more generally in the semantics that underlies the propositional logic. Functional completeness is a really interesting property. You can prove it for a range of different logics, and what it tells you is really the sort of minimum number of syntactic items you can get away with in order to produce a system that can do everything that propositional logic can do. Why might you care about that? Well, you might have sort of software engineering constraints that require you to have very efficient like a sort of very efficient basis for building it. You know, you might only be able to use two items that you can manipulate, and then just using those two items, build a whole range of other items or a whole range of other functions. This is going to give you some insight into how to do that. And in fact, that is precisely what happens in a lot of computer software engineering. The other reason you might care about this is that there are lots of other functions to choose from when you're thinking about argument and reasoning that we don't necessarily include inside propositional logic. And sometimes some of those functions might actually be useful for doing argument, and some of them might not be very useful. And so thinking about which ones are useful and why, I think gives you a better insight into what it is that we're doing when we're building a logic that models rational argument, and why it is that we use the specific functions that we do in order to model some of the things that we're dealing with inside argument in rational terms. One of the further interesting things, I think, is that this is going to give you some insight into why the conditional is the way it is inside propositional logic. So a lot of people, when they meet the conditional and they see that it's true when the thing on the left-hand side of it is false, they get worried because that seems really counterintuitive. That seems right, and there are lots of people in philosophy and computer science and mathematics who've worried about the status of that conditional. But if you look at the sort of candidate functions that we have inside this sort of semantic framework for representing something that can do the kind of things that the English if-then can do, it's very hard to see what else we could use inside that function space except for the kind of truth table that we currently do use for the conditional. Because that truth table at least gets this right. It's false when the thing on the left is true and the thing on the right is false. And that's what we get from the English sentence, and that's what we want to model semantically when we're working inside propositional logic. There isn't really another function that can do as well as that with respect to modeling the English if-then statement. And so that's why we tend to use that conditional. It's not perfect, we realize that, but it's kind of the best you can do within this semantic framework. And that, of course, has led people to wonder, how much should we actually be using this semantic framework? Is there another way to build a semantics for a logical language or a system of language more generally that has a greater capacity to represent the kind of reasoning that we're actually doing in English? And if you ever get interested in advanced logic or taking more logic courses, one of the things we really look at is whether or not you can change the underlying assumptions of how the entire logical structure works by manipulating the semantics in certain interesting ways to produce radically different kinds of logics that have conditionals that behave in weird and wonderful ways. For now, the things that I want you to focus on from this bonus lecture: first of all, there are 16 distinct functions in propositional logic. Second of all, you can build any of those functions from a certain minimal set, namely things like the negation and the ampersand, negation and the conjunction. Interesting to think about which other things you might be able to build everything from. And the third thing is that you can use any of these 16 functions in precisely the normal way that we've been using the 5 sort of privileged functions that we focus on in propositional logic, which is to say that you can compute complex values using any of these functions in exactly the same way. You try and work out how that function works based on the information coming in from A and B, like work out what kind of box that function is, what it's actually doing to the information when it comes in to get an output, and then based on working that out, apply it to a range of different arguments should you need to. All right, that's all for this bonus lecture. Hopefully you get a bit of a sense of how functional completeness works, and it gives you a little bit of an insight into how some of the trickier questions in your assignments, problem sets, multiple choice quizzes, and exams might be working. All right, thank you very much.